Now that we have seen many examples of Jordan measurable sets, the last topic that we will cover under Jordan measures is its deep connection with the theory of Riemann integration. So let's recall what's the definition of a Riemann integral of a function. So if f is a function defined on an interval a b to say the real numbers r, and it's a bounded function, then one can define the Riemann integration a to b fx dx is a real number called the Riemann integral of f, defined as follows. So I'm going to just give you a brief recall of the original definition of the Riemann integral. So the intuition is pretty straightforward. So if you have a function between points a and b, then you can partition this interval a b into subintervals of possibly different length, but that's not important. So here you have points x0, which is equal to x1, then which is equal to a, then x1, x2, x3, and so on, and b is equal to xn. So you have n plus 1 points dividing the interval, the segment AB, into subintervals, and we put delta xi to be the difference xi minus 1. So I is equal to 1 to n here, and then for each subinterval you choose a point, call it t1, t2, and so on, t3. So for each xi, for each subinterval xi minus 1 xi, choose a point ti in this interval, and in this way we form what is called a tagged partition. So this is called a tagged partition of AB, and then one defines the sum. The Riemann sum is defined to be f of the value of f at this point ti multiplied by this length of the interval del xi I from 1 to n. So this is the Riemann sum of f with respect to the partition P, that the tagged partition P that we have defined here. So this is called the Riemann sum of f with respect to the tagged partition P, and the Riemann integral a to b fx dx is the limit of these Riemann sums fp. The limit is taken over all partitions P, tagged partitions, and the norm of the partition goes to 0, where this norm of the partition is simply the supremum of this del xi's I equal to I from 1 to n. So as the size of the intervals in the partition goes to 0, you take the limit of these Riemann sums, and if this limit exists, then this is called the value that you get as a limit is called the Riemann integral of f. So this is the original definition of Riemann, but unfortunately it's not very convenient in practice, when you want to actually compute the integral, the Riemann integral of say a continuous function over an interval, then this tagged partition definition is not very convenient to use. So an equivalent formulation is given by Darboux integration. In this integral, the Darboux integral is defined using a similar partition, but rather than using a tagged partition, it considers the maximum and minimum value. So over this interval, over a subinterval of this partition, what is the maximum and minimum value of the function f that it takes on this subinterval. So here this lower part, the lower horizontal line can be denoted, say, x lower star and f of x lower star rather, and this is f of x upper star. So this is the supremum of the values of f over the subinterval, and the lower star, fx lower star, is the infimum of the values of f over this interval. So the Darboux sums, the Darboux integration is defined using the Darboux sums, upper and lower Darboux sums. So the upper one, upper Darboux sums, is defined UF with respect to a partition P. This is defined to be the sum from 1 to n f x I, and the ith partition take the maximum value of f, fx upper star, and then multiply it with the size of the subinterval. So this is the supremum over xi less than or equal to, sorry, xi minus 1 less than or equal to x less than or equal to xi f of x. This is the supremum value of f over this subinterval. And the lower Darboux sum is given by the same sum, but instead of f upper star you use f lower star, and this is the infimum of fx as x ranges between the interval xi minus 1 to xi. And the Darboux integral is defined, integral f b a to b fx dx is defined if the limit as the norm of the partition goes to 0, u fp is equal to the limit as the norm of the partition goes to 0 as of the lower Darboux sum, and this is equal to a to b fx dx. So these two limits are the same. Now a fundamental theorem of integral calculus says that a function, a bounded function f from an interval a b to r is Riemann integrable if and only if it is Darboux integrable. Now the definition due to Darboux is more convenient to use, and in fact this theorem not only says that when f is Riemann integrable if and only if it is Darboux integrable, but also that the values of the integrals are the same. So the values of the integrals of the Riemann and Darboux integrals. Darboux integrals are the same in this case. So one can use the Darboux definition, and it is more convenient to use, as we will see. So the connection with Jordan measure is the following theorem, which says that if E, a subset of R, is a bounded subset, then E is Jordan measurable if and only if the indicator function of E, chi E, which is defined as 1 if x belongs to E and 0 otherwise, is Riemann integrable, in the sense that integral a to b chi Ex dx exists, meaning that it's a finite number where E is a subset of this interval a b. So because E is a bounded subset, we can always find a and b such that A is a subset of this interval a b, and in this case the indicator function from a b to the reals is well defined, and then we can talk about the Riemann integral of the indicator function of E. And this statement says that E is Jordan measurable if and only if this integral exists. So this is what we want to prove. This is the first connection that we want to prove with the Jordan measure. So let's try to prove this, but before we prove this, we will make another equivalent reformulation of Darboux integrals, which will be more convenient for our purposes, and in fact it will give us an idea how to define the Lebesgue integral when we talk about Lebesgue measurable functions. So the equivalent reformulation of Darboux integrals depends on the definition of the so-called piecewise constant functions. So a function g from an interval a b to R is called piecewise constant if there exists a partition of AB into finitely many intervals, finitely many subintervals. Let's call them ik, k equal to 1 to n, such that this function g takes a constant value ck on each ik. So ck belongs to R on each ik for k equal to 1 to up to n. So this is called a piecewise constant function. So for a piecewise constant function, we define the Riemann-Darboux integral as follows. So I will denote this as a to b with a cut in between to show that, to distinguish it from other functions. So the Riemann-Darboux integral for a piecewise constant function g is given by the sum I equal to 1 to n ck m ik. So this is a definition, and one should show, as an exercise, one should show that this definition is independent of the partition used, independent of the partition ik. So which means that if you have another partition I prime k, then the values of g, the constant values ck prime of g on those ik primes, and will give you the same result when you sum up this ck mik's for any other partition. So this is left as a as an exercise for you, and it's not a very difficult exercise to show. So this is an unambiguous definition for the Riemann-Darboux integral of a piecewise constant function. Now we define for a bounded function f from ab to r, the upper Darboux integral which is denoted ab with an upper bar fx dx, and this is defined as the infimum of functions which are pointwise less than or equal to f, where g is a piecewise constant function, and you take the Riemann-Darboux integral for the piecewise constant function g. Similarly, the lower Darboux integral is denoted by ab with a lower bar fx dx, and this is the upper one is going to be f less than or equal to g piecewise constant, and the lower one will be given by g pointwise less than or equal to f g piecewise constant, and you take the Riemann-Darboux integral of the piecewise constant function g. So these are the upper and lower Darboux integrals, and it can be shown without much difficulty again that the lower Darboux integral a to b fx dx is always less than or equal to the upper Darboux integral. And when the equality holds in this inequality, we call this the common value as the Darboux integral. So when equality holds, this is that the lower Darboux integral is equal to the upper Darboux integral, then this common value is denoted by the integral of fx from a to b. And in fact, one can also show that the lower Darboux integral is exactly this the limit over all partitions with the norm of the partition going to 0 of the lower Darboux sums, and the upper Darboux integral is precisely the limit over partitions with the norm of the partition going to 0 of the upper Darboux sums. So this definition is just a reformulation of our previous definition with respect to the upper and lower Darboux sums, but nevertheless this will be more convenient to use for our purposes.